Hello and welcome back. In this video we'll start section 5.2, which is on the binomial distribution, which is a type of discrete probability distribution which was introduced in the last couple of videos. So binomial distribution, when we look at the word binomial, the prefix bi means two, and the nom here means name. So this is going to be a distribution that's essentially counting two different things. We'll have successes and failures. So a binomial distribution is going to be any procedure that satisfies the following four things. And one thing to keep in the back of your mind is, let's say that we're flipping a coin and we're counting how many heads we get. The first thing to notice is that binomial distribution has to have a fixed number of trials. So if we're flipping coins, we've got to flip the coin exactly n times. So maybe we flip the coin 10 times or 100 times, as long as that number is fixed. Each time we run this, each one of our trials has got to be independent. They can't affect one another. So if we're flipping a coin, what a coin was flipped last time, whether it's heads or tails, does not affect the next time. Also, there must be exactly two types of outcomes. What we'll call successes and what we'll call failures. So maybe what we're interested in is heads. So we'll consider any flip that results in a head. In heads is called a success, and anything that is not heads is going to be a failure. Now, this is just terminology. Successes and failures don't have to indicate good results and bad results. It can refer to anything. And then the last thing is the probability of success in each trial has to be the same. So for instance, if we're flipping different coins and some of them are not fair and they don't land heads and tails equally, this won't work. We have to flip coins that have the same probability of landing heads each time. So let's look at another couple of examples. The first one is the number of free throws made in 10 attempts. This is in fact a binomial distribution. We're shooting 10 free throws. Each of our free throws are independent from one another. They don't affect one another. There are two types of outcomes. Either we make the free throw or we don't. And the probability of success is going to be the same in those 10 attempts, barring hours and hours of practice in between them. Here's another one. This is the number of sixes rolled out of 4 dice. So we'll roll 4 dice and we'll count how many sixes were rolled. So again, there's a fixed number of trials, as in we're rolling exactly 4 dice. Each die is independent from each other. There are 2 types of outcomes in here. And even though there are 6 sides to a die, if we're only counting the number of sixes, we could call a 6 a success, and anything that's not a 6 is called a failure. So even though I could also count the number of 1s, 2s, 3s, and 4s and 5s, in this situation, if I'm just counting the number of 6s, anything that's not a 6 would be considered a failure and will only count the successes. Here are a couple that aren't probability distributions. So this first one, the number of coin flips until the first heads comes up. So we're just flipping a coin and we're counting how many times we have to flip before we get a heads. This does not have a fixed number of trials. Maybe it could take 2 flips, maybe it could take 5, maybe we get heads on the first one. Since there's a different number of trials going on, this is not a binomial distribution. It's another type of distribution. Here we'll say the bucket has 10 blue balls and 10 red balls, and we'll draw 5 balls out of the bucket without replacing them, and we'll count the number of red balls. Okay, so here we have a fixed number of trials. We're only drawing 5 balls, but each time we draw a ball, we change the balls that are left inside of the bucket. So if you draw a red ball out, now there are fewer red balls in the bucket, which changes the probability at each stage. So the individual trials are not independent and the probabilities change. So this is not a binomial distribution. The probabilities are not constant. So there's a couple of different ways that we can have distributions. These are perfectly valid distributions, they're just not binomial distributions. Some notation, we'll normally call S, we use a capital S for success and a capital F for failure. And the probability of getting a success on any one trial, so this is just for one trial, the probability of success we normally call P, and the probability of failure we call Q. And these guys have an interesting relationship. These are going to be complements of one another. You either succeed or you fail. There's no in between here. So since we are certain to get either a success or a failure, these are complements of one another, and that means that their probabilities should add up to 1. Generally, we're only given P. In a question, you're generally only given P, so we would normally write Q as just going to be 1 minus P. And this is just a quick way of calculating this. We normally use N to represent the number of trials. So for instance, the number of coin flips that we're making, the number of free throws that we're shooting, the number of dice that we're going to roll. And X will be the number of successes that we're looking for, with probability of X being the probability that we get exactly X successes. And one thing to notice is that if N is the number of trials and X is the number of successes, N minus X will be the number of failures. And on top of this, what are the possible values for X? Well, we could succeed no times, or we could succeed every time. So X would have to be somewhere between 0 and N. If we flip 10 coins, we can't get 15 heads. That doesn't make sense. So let's write down a few things for this example. Let's go back to free throws made in 10 attempts. First of all, we're shooting 10 free throws, so N here is going to be 10. A success, maybe this is going to be a made free throw. And a failure, we'll just call a missed free throw. This the complement of making a free throw. The probability of success. So we're not necessarily told this in the question. In order to calculate this, we would need to be told this. This is not something that we just know. So if we assume that we are Steph Curry, over his lifetime, he's made 90% of his free throws. So here, the probability of success for Steph Curry would be 0.9. So the probability of failure, the complement of this, is going to be 1 minus 0.9, which is 0.10. And this makes sense logically. If he's made 90% of his free throws, he'll have missed 10% of his free throws. And then X, the number of free throws he could make in 10 attempts, would be somewhere between 0 and 10. So you can ask, how do we actually calculate probability? So if we know that the probability of one success is going to be 90%, as in 0.9, you could ask, well, what's the probability that Steph Curry makes exactly 7 free throws? It turns out that we've got a formula, and this is the formula. It is big, it is messy, but it is not too hard to remember, and I'll go through the individual parts of this. So let's apply this formula first. Let's just use this formula once in a fairly simple case, and then we can, and then I'll break this down a little bit more. So let's look at the probability of rolling exactly 2 6s in 4 rolls. Okay, so we're rolling 4 dice. So n here is equal to 4, and then our 6s. This is what we're counting. So we'll call S is going to be getting a 6, and so a success is getting a 6, and a failure would be not getting a 6. Furthermore, the probability of rolling a 6 on a die, well, there's 1 6, but there's 6 potential sides, so we've got a 1 in 6 chance of rolling a 6. So that means that the probability of getting a failure will be the rest of the probability, 5 out of 6. Okay, and then we want to know what's the probability of getting exactly 2 6s. So here, x is going to be 2. So then we'll just plug everything into this formula, and we will see what we get. So let me do this on the next page. So the probability of getting exactly 2 6s, let's pull this up, will be 4 factorial. Let me write down the original equation as well. This will be a little bit easier. N factorial divided by n minus x factorial times x factorial times p to the x times q to the n minus x. So let's fill in some of these numbers. So we have 4 factorial divided by 4 minus 2 factorial times 2 factorial times 1/6 to the 2nd power, because x is 2, times q, which is going to be 5/6, to the n minus x. So this is 4 minus 2 power. A lot of this simplifies, so let me simplify this down here. 4 factorial is 4 times 3 times 2 times 1. 4 minus 2 is 2 factorial, so that's 2 times 1. 2 factorial is, again, another 2 times 1, not 21, 2 times 1. 1/6 to the 2nd power, well, that's 1 over 6 squared. And then over here we've got 5/6 to the 2nd power, so that'll be 5 squared over 6 squared. Simplifying some more, the 2's will cancel out with this 4, and then we can multiply all this together to get 3 times 2 times 5 times 5 over 6 times 6 times 6 times 6. I can cancel out a little bit more, so this is going to be 25 over 216. So this is going to be a little bit less than 1/8. This was a big mess, but we can just substitute these numbers in and plug them in. Google can help solve factorials for you, and also raise probabilities to 2 powers. Google can take care of a lot of this. So what I want to do is I want to show you a little bit of where this comes from. So if we want 2 6s out of 4, so if a 6 is a success, there's a few different ways that we could come up with 2 6s out of 4. We could get success, success, failure, failure. We could get success, failure, success, failure, or success, failure, failure, success. We could keep going. We could get a failure, success, success, failure, failure, success, failure, success, or failure, failure, success, success. This would be all 6 ways of ordering the successes and failures that we could come up with. We could roll our 2 6s first and our non-6s last, or in any order that we want. But we see that there's 6 orders. Where did this come from? Well, if we remember, there are 4 factorial ways to arrange things, but if we have 2 pairs of duplicates, we need to divide by 2 factorial and 2 factorial. So this is the number of ways to arrange successes and failures. I'm just going to abbreviate that. So this 4 factorial divided by 2 factorial divided by 2 factorial comes exactly here.